Hey guys, welcome back. It's Mrs. Webb again. So today we're going to add on to that idea of projectiles, projectile motion. Last time we talked about horizontal projectiles. Previously we were talking about free fall problems where the object was moving in just a one-dimensional plane. Now we're going to kind of put everything together and look at the complete trajectory of a projectile as it travels up and then down in a two-dimensional plane. So just a couple of kind of review points for you guys from the previous lesson. Remember that we defined a projectile as any object that's moving through the air. So it could be a football, it could be a boulder that launches itself on the way down in a rock slide. It could be a biker that's launching itself from the edge of a cliff, like in our last example. And there's a couple of things that we assume, a couple of assumptions that we make. We said that the object's velocity in the air is made up of the x and the y component. So it doesn't have an official velocity that we would record the object moving at, but that velocity can be broken into an x and a y component. The x component, we said, is moving at a uniform rate, so acceleration is 0 in the x direction, and the velocity does not change. And then we said that in the y component, in the y direction, the object is continually accelerating toward the Earth at a rate of 9.81 meters per second squared. So the object in the y direction is moving at a uniformly accelerated rate. And then the final point was that regardless of the direction of motion for the object, we assume that it's moving under ideal conditions and it will not be affected by outside forces such as air resistance and things like that. So we don't look at that. We just assume that it's traveling free floating without being obstructed by any sort of outside forces. The only outside force, I suppose, that's moving the object is gravity, and that's what's causing it to accelerate toward the Earth. But aside from that, there's nothing else that's impeding the object's motion. So just like in the previous lesson, I've got an image here for you just so that you can get an idea of what's happening. So here's my object at the beginning of its path. It's going to be launched at a certain angle, and it's a little bit hard to see for you, but this angle here, that's your theta. Generally, that angle will be referenced to the horizontal or to the ground level. So this is the velocity of my object as it's, if it's a football that's being kicked for a field goal or something like that, or it's a baseball that's being hit by a bat. It's going to leave at a certain velocity. It's going to travel up a certain distance, displacement in the y direction, and then it's going to reach an apex. It's going to reach a maximum height, and that maximum height is going to be the point where the y component of the velocity has gone to 0. It's still moving in that x direction, so that it's still being propelled forward in the x direction. But for a brief instant, it's coming to a stop in that y direction. And then almost just as quickly, it starts to accelerate back toward the Earth. Okay, so a couple of things to note here. This original velocity vector that the object leaves at, this velocity vector is at an angle. So that means that there is an x component and there is a y component. And the sum of these two components is going to give us this resultant velocity. So you can see the x component here is the blue arrow. The y component is the orange. If you notice throughout this entire trajectory, the length of this blue arrow never changes. Up here, the blue arrow is equal to the purple resultant velocity arrow because the motion is in the same direction. And then here we see the blue arrow again as the ball starts to descend toward the ground, right? So the magnitude of this arrow never changes. The other thing to note is that the y component, the orange component, initially it's propelling the object in the upward direction, right? And as the object is rising, you'll notice that the length of this y arrow, of this orange arrow, is getting shorter and shorter and shorter, and there comes a point where it disappears. That's the point where the object has reached its maximum height. And almost as quickly it's going to start falling toward the earth. And as soon as it's falling toward the earth, you'll notice that because it's falling toward the earth, now the y component is pointing downwards because the motion of the object is traveling down toward the earth. It's not moving upward anymore. And all of a sudden we have this teeny arrow, orange arrow, that pops out. And as the object falls toward the earth, the length of that orange arrow gets longer and longer and longer. So the third thing to note here is that originally this original velocity, resultant velocity, is pointing up. So it's showing you the direction that the object is traveling. It flattens out. Now it's moving horizontally, and then it's moving back toward the earth. So now the purple arrow is pointing toward the earth. If the object takes off from this height and it lands at this height, you'll notice that the length of this purple arrow is equal and opposite to the length of the purple arrow at the end, right? And the orange arrow is equal and opposite to the orange arrow, the y vector or component at the end. And the blue arrow is the same throughout. Now, if this was a scenario like our biker launching itself from the cliff, and the biker launched itself in an upward direction, it's not going to land at the same spot. So if it were to continue traveling past that original launch point, then this velocity is going to continue, the overall resultant velocity is going to continue to grow longer or faster than the original launch velocity because it's continuing to accelerate toward the earth. And this y will continue to grow as well as the resultant velocity gets larger and larger and larger and larger. Okay, so that's kind of the breakdown of that trajectory in the upward motion and then in the downward motion. And so we've still got information happening in two directions. Again, the linking component is your time between the x and the y. So I've got an example for you guys here. In this case, again, more people launching themselves out of things. So we have a knight. The knight is launched out of a cannon elevated 20.0 degrees above the horizon. The velocity of the knight is 2.50 times 10 to the 2 meters per second. And we want to calculate a couple of things. We want to figure out what's the maximum height of the object, or of the knight, when it reaches that maximum height. We want to figure out what is the length of time the knight will be in the air. Another way you might see that written is what is the hang time. So we can also, you probably, the most common place I've heard about hang time is when you talk about basketball players and their hang time as they're, going in for a dunk or something like that. And then the range of the knight. What is the range? And remember, the range is the total x displacement while that knight is flying through the air. So here's my scenario, or my setup, my diagram. My knight, they've told me, is angled at an angle of 20.0 degrees to the horizon. The horizon is just the ground, another way of saying the ground. The knight's going to launch itself, or he's going to be launched at a velocity initial of 2.50 times 10 to the 2 meters per second. The knight eventually will travel this general trajectory, and then he'll start to make his way down to the ground again, and hopefully land somewhere over here, ready for battle, or maybe on a launch pad or something like that, or a crash pad or something like that. Now, because my knight is moving in this general direction, I'm saying that up is positive, and left is positive, just because that's the direction of motion of the knight here in this first half of the trajectory. The other thing I know as well is that when the knight does reach its maximum height, the velocity in the y direction is going to be 0, right? So if we go back to our original diagram up here, Remember that this orange y vector gets smaller and smaller and smaller, and at the max height, it disappears for a brief instant because the object is no longer moving in the up and down direction. And then almost as quickly, it starts to fall back toward the Earth, and that y direction pops up again. So at this max height spot, the velocity in the y direction specifically is going to be 0. So because the knight is launching it himself or herself at this angle, I need to figure out, or I know that there's going to be an x component and a y component to the knight's velocity, and I need to figure that out so that I can work with the two aspects of the knight's motion. So I know that in the x direction, just like when we were doing 2D motion previously, this is my resultant vector, the knight's total velocity. The x component is going to start here at the origin, at the tail of the total velocity. It's going to move out, and then the y component is going to travel up to the tip of the resultant vector. And ideally what we're doing is we're moving these x and y components around so that we can sandwich this angle of 20 degrees in the middle and create a triangle around it. So that means that with respect to this 20-degree angle, the x component is adjacent. It's beside the angle. So that means I'm going to use cosine. So I take 2.50 times 10 to the 2 meters per second times cos 20, and I get 234.92, meters per second. The y, this is my y here, it is opposite to my 20 degrees, so I'm going to use sine. And so I take 2.50 times 10 to the 2 meters per second times sine 20 degrees, and I get 85.505038 meters per second. I'm not going to round anything at this point. I want to hold on to all my numbers so that I don't end up with rounding errors at the end. Now I'm going to set up, oh, I zoomed in, sorry. Now I'm going to set up my knowns. So I know that the first thing they're asking me is what is the maximum height? And so maximum height is in the y direction. So I'm going to set up my known variables in that y direction. I know that displacement in the y, the maximum height is what I'm looking for. I know that at the top, when I do reach that maximum height, my velocity in the y direction will be 0. I know gravity is 9.81 meters per second, and remember that I said that up was positive since the object is moving in this upward direction, which means that gravity is going to be a negative 9.81 meters per second. Now remember, the negative doesn't imply anything other than the direction that that vector is pointing. The initial velocity in the y direction is 85.505038 meters per second, so that's what I just calculated over here. And the only thing I don't have here is my time. So if I look at my list of kinematics formulas, the only formula that does not use time is this one. The F squared is equal to the initial squared plus 2 gravity times displacement. And all of this is in the y direction, so I've got my little y subscripts. I'm going to plug in all my information. So I've got 0 meters per second squared times 85.505038 meters per second squared plus 2 times minus 9.81 meters per second times displacement in the y direction. And if I rearrange, I end up that in the y direction, the knight is going to displace itself 373 meters up. That's going to be the displacement of the knight when he reaches his max height. Now the second question asks, what is the length of time in the air? So what is the hang time? Now length of time is the time that it takes the knight to go up and to come back down. So what I need to know is, well, how long does it take the knight to get to the apex of the trajectory, or the top of the trajectory? How long does it take the knight to reach its max height? So I know my velocity initial in the y direction. I know my velocity final. I know gravity. Now I know my displacement in the y direction, so I can figure out what is my time up. And really, at this point, I've got my pick of the litter in terms of formulas. I chose to use this formula only because my velocity final was 0 meters per second, and so I can just take this term here out of the equation. And that leaves me with 373 meters is equal to negative half times negative 9.81 meters per second squared times time squared. If I rearrange my formula, take the square root, I get that the time up is 8.72 seconds. Now that's a time for the night to travel to its max height. If we look at our diagram, we'll note that the night is starting here at ground level, leaving, and when the night eventually falls back to the ground, the night's going to land at the exact same point that it took off. So that means that because the night is accelerating at 9.81 meters per second up, and it's accelerating at 9.81 meters per second down, the rate of the night slowing down is equal to the rate of the night speeding up. And if that's true, and the night is stopping its path at the same spot that it started its path, that means that the time down is going to be equal to the time up. So as soon as you've got, a image like this, where you've got the trajectory starts at the same place as it finishes off in the y direction, the time up will equal the time down. And so the nice thing about those problems is that it doesn't really require any more calculations or kinematic formulas. All I need to know is if my time up is 8.72 seconds and my time down is 8.27 seconds, I just need to double this time that I calculated. So since the object takes off and lands at the same height, time up equals time down, and so my total time is 17.4 seconds. Now the final bit to this puzzle is what is the range, right? And I want to figure out what is this distance in the x direction that the night is going to travel. So what I need to know, I know that in the x direction, this component is not going to change. In the entire trajectory, that x component is going to stay the same. And now I know that the total hang time, the total air time the night has, is 17.4 seconds. So in the x direction, the night is moving at a uniform rate. So I know my velocity in the x direction. I know my time that the night is traveling in that x direction. And now I can solve for the displacement in the x direction. So I use velocity x equals displacement x over time x. I rearrange for my total displacement x, sub in my numbers, and I get that the total displacement in that x direction is 4.10 kilometers. That's how far the night will travel in the x direction, the range. Slightly more complex problem. We have here a soccer player kicks a ball at an angle of 37 degrees to the horizon, or to the horizontal, sorry, with a speed of 22.0 meters per second. The ball lands on top of the net, and the net is 2.44 meters off the ground, or the ball, when it lands on the net, is 2.44 meters off the ground. We want to find what is the maximum height of the ball and how far from the net the player was when he kicked it. Okay, so how far from the net the player was when he kicked it may be kind of a weird thing to think about right now. So the first thing I want to do is I want to draw my picture. If I can picture what's going on, it makes the calculation so much easier. And I've said this continuously since we started physics, but if you can take a moment to just kind of picture it, it helps set up how you're going to go about solving this problem. So we've got our net over here. Here's my ball at some place, away from the net. The problem has told me that originally the soccer player is going to kick the ball with a velocity of 22.0 meters per second at an angle of 37 degrees to the horizontal, right? So that's the angle that the ball is being kicked at. It's going to fly up in the air, and eventually when it lands, it's going to land on top of the soccer net, and that net is a height of 2.44 meters off of the pitch. I want to figure out what is my height in the y direction, and I want to figure out how far away was the soccer player from the net when he kicked it. Now, that means that if I'm looking for how far away was the soccer player from the net, That's asking me for the distance along the horizontal, which means I'm looking for the range that the ball is traveling in the x direction. And so I know that this velocity is an angle of 37 degrees, which means I have to figure out the component in the x direction and in the y direction. So I'm going to start here at the beginning, at the ball, at the projectile. I'm going to draw my vector out and then up, right? So that I sandwich this 37 degrees and I make a triangle around it. And you can see that in order to do that, I have to move toward the right first, and then I have to travel up. So moving toward the right, that gives me my x component, which is adjacent or beside my 37 degrees. So that means I'm using cosine. So I've got 22.0 meters per second times cos 37. And I get that the x component is 17.569981 meters per second. Now the y direction is opposite my 37 degrees. So that means I'm using sine. So 22.0 meters per second times sine 37. And that tells me that my y component is 13.23993 meters per second. Now I've set everything up. I don't really know anything else at this point. For this beginning portion here, what I want to figure out is how high is the ball moving, right? So I'm looking at things in the y direction. Because the object's traveling in this general direction, I've said that my up is positive since the ball is traveling up, and I'm saying that my right is positive since the ball is traveling toward the right. So in my y direction, I know the y component of the velocity initially is 13.23993 meters per second. I calculated that here. I know that when the ball reaches its maximum height up here for a brief instant in time, that velocity in the y direction is going to go to 0. So my v final y is 0 meters per second. And I know that as soon as the ball leaves the soccer player's foot, it's going to start accelerating toward the earth at a rate of 9.81 meters per second squared. Negative, because that acceleration is pulling it back toward the earth. As the ball is moving up, that acceleration is pulling it back up toward the earth, which is why the trajectory starts to curve back toward the earth, right? And so since I set up is positive, my acceleration vector is going to be negative. And I'm looking for what is that displacement in the y direction. So I've got velocity initial, I've got velocity final, I've got gravity. I'm looking for displacement y. First thing I'm doing here, and I'm looking for time up. So first thing I did was I took my gravity is equal to my total velocity divided by my total time. That's velocity final minus velocity initial divided by t up. I'm rearranging to solve for the time that the ball is in the air. So I plug my numbers in. Final velocity is 0 meters per second minus 13.23993 meters per second divided by minus 9.81 meters per second squared. And I get that the ball takes 1.3496361 seconds to reach its max height. So that's the first part. Now the second part is I want to figure out what is that max height. Well, I know that by the time that it gets to that max height, this final velocity has gone to 0. So I'm using displacement y is equal to v final times time minus 1/2 gt squared. This term goes to 0. I'm going to plug in my numbers. So minus 1/2 times minus 9.81 meters per second squared times my time up. And I get that my displacement in the y is 8.393. Sorry, I said that wrong. Is 8.93 meters up. That's how far the object is going to displace itself in the upward direction. Okay. Now, the next thing is this. So I've figured out kind of this first half of the trajectory. The trick here, compared to in the other problem, is that you'll notice that the ball doesn't come back down all the way to the pitch, which means that the ball gets hung up at some point during its downward trajectory, right? So I can't assume that time up is equal to time down here, because at some point that ball gets interrupted and it gets stopped before, ground level. So in the second half of the problem, because now the ball is making a downward displacement, is moving itself in the downward direction, I'm going to say that down is positive. And I'm going to continue saying right is positive because it's still moving in this right direction. It's just that now it's falling back toward the earth. So what I want to figure out is I want to figure out how long is this ball going to fall before it gets hung up on the soccer net. So to figure out my time down, I know that gravity is 9.81 meters per second squared. I've said that down is positive, so this is positive 9.81 meters per second squared. I know that initially here, when the ball initially starts its downward path, that velocity here is going to be 0 meters per second in the y direction. So v initial y is 0 meters per second. And the other thing I know is that the distance the ball is going to fall is the total height, the max height, the 8.93 meters, minus where the ball ends up, the 2.44 meters. So that means that the ball falls a distance of 6.49 meters from the time that it reaches its max height, and then it gets caught up in the net. And the reason I want to do this is because the second part that the question asked me is how far from the net was the player when he kicked the ball. So if I'm going to figure out this range, this distance in the x direction, I need to know what's the total time that the ball is in the air, because that time is what links my y direction to my x direction. And I ended up using displacement y is equal to v initial times time plus 1/2 gt squared. This v initial term goes to 0. I'm plugging my numbers in, rearranging for t, and I get that the ball falls for 1.15 seconds down. This is how far it's falling down, which means that the total time the ball is in the air from the time it leaves the soccer player's foot to the time it gets hung up on the net is the time down plus the time up. So the 1.15 seconds plus the 1.35 seconds. And that means the total hang time is 2.50 seconds. Now that I know this total hang time, now I can solve for what is the direction, or what is the displacement in the x direction. So I know that the original x component is 17.569981 meters per second. I solved for that originally. I know my total time that the ball is in the air. I know that in the x direction we're moving at a uniform rate, so I can use Vx equals total displacement in the x direction divided by total time. I rearrange for my displacement in the x direction, plug my numbers in, and I get that the ball moves 43.9 meters to the right. That's how far the ball displaced itself. So that's definitely a little bit more of a challenging problem because the ball is starting at one point and it's ending at a different point in the y direction. Which means that there's just a little bit more calculation that has to take place. Now the other thing, guys, too, is note that with all these problems, I used these specific formulas, I took this specific approach, but there's also different ways that you guys might see the problem and that, other students might see the problem that will get you to the same answer. So there, like I said, when we were talking about the kinematics formulas originally, it's not just a one formula fits all kind of scenario. You could get to the same, displacement in the y direction using a different formula. So that's it for now. We're going to practice this when we see each other. Bring any questions you might have to class with you. And as always, guys, I hope you're doing well. I hope you're taking care of yourselves, and we will chat very soon. Bye for now.